Okay, let's unpack this. What if the models we spent years training to create stunningly realistic images, to conjure visuals out of thin air, are actually much, much better at seeing and understanding the visual world around them than we thought?
Mm.
Not just generating it, but actually perceiving it.
It almost feels like a hidden superpower, right? Like we built them to synthesize, to imagine pixels into existence. But this paper makes a really compelling case that this process maybe inadvertently taught them something fundamental about how the visual world is structured.
Absolutely. Welcome to the Deep Dive. Today we're plunging into a fascinating new paper, gen2seg, Generative Models Enable Generalizable Instance Segmentation.
Right.
At its heart, it takes these incredibly powerful generative models, the ones behind those jaw-dropping images, and cleverly redirects their learned abilities to a core perception challenge: instance segmentation.
Yeah, and instance segmentation is, it's more than just identifying a cat in an image. It's finding every single cat in that picture and drawing a precise outline, a mask, around each one individually. It's pretty fundamental to understanding a scene in detail.
And traditionally, getting really good instance segmentation, especially for any object you might run into, has been incredibly data hungry. We're talking needing data sets with millions, sometimes even billions, of carefully drawn masks.
Billions, yeah. And even then, these models can struggle with objects or styles they've never explicitly been trained on. It's a real bottleneck.
The challenge is generalization, isn't it? Can your model segment a specific, maybe like an unusual object instance if it wasn't in its massive training set?
Exactly. Or can it handle artistic styles, different lighting conditions, or entirely new categories it's never encountered before?
So based on the stack of sources you've shared with us, our mission in this deep dive is to really dissect this gen2seg paper. We want to grasp their core hypothesis that these generative models hold this sort of hidden key to visual understanding.
Right.
We need to explore their, frankly, really innovative technical approach, and then look at the surprising experimental evidence that seems to back up their claim. It feels like they've found something significant about the visual knowledge embedded within these, generative giants.
Yeah. And the first major innovation is how they redefine the problem itself. So instead of predicting binary masks, which is the standard output, for instance, segmentation.
Right, where each pixel is either 0 for background or 1 for the object.
Exactly. They completely rethink it. They treat instance segmentation as an image-to-image translation task. The model takes the input image and outputs a different image.
Okay, an image-to-image task. And what does this output image actually look like?
Well, in the output image, every detected object instance is colored with a unique, pretty much uniform color, and the background is just black. Think of it like a segmented map where each distinct region gets its own color, but the coloring itself is part of what the model outputs. It's not something you predefine.
Okay, I can see how that aligns with a generative model's strength. I mean, they're built to produce images, so you're mapping an input image to an output image.
Yeah.
But how do you train it to assign those colors correctly?
Right.
So that all the pixels of one object are the same color and different objects get different colors, especially if you never tell it beforehand. Okay, make the chair blue and the table red.
That's really the core academic cleverness here, and it's all wrapped up in their novel instance coloring loss, or mathcal. This loss function is specifically designed to guide the model using just the ground truth instance masks we already have.
Okay.
But it's phrased in a way that encourages this specific coloring behavior in the output image. It basically teaches the model to group pixels into distinct instances just based on visual coherence and separation using the loss structure.
Let's break down this loss then, because it really sounds like the engine driving their whole method. You said it has 3 components.
Yes, 3 main parts, and each plays a crucial role in getting the result they want. The first one, and they argue it's the most critical, is the intra-instance variance loss.
Instance variance. Okay, so variance within a single instance.
Precisely. Its whole job is to force the model to predict colors for all the pixels belonging to a single identified object instance that are as close to each other as possible.
Right.
It really pushes for uniform color within that object's region in the output image.
Makes sense.
They use a smooth Elevale one loss, which is a bit technical, but it basically means it's less sensitive to a few outlier pixels getting slightly off colors, which helps make the training more stable.
Right.
And the paper explicitly says if you remove just this term, the whole system collapses. It's absolutely fundamental to making the model learn to group pixels together properly.
Okay, so the first term says, make everything inside one object the same color. Got it. But that doesn't stop the model from just making all the objects the same color, right? How do you make sure different objects get different colors?
That's where the separation components come in. Good point. The second term is the inter-instance separation loss. This one works to push the predicted colors of pixels outside a given instance away from the average color that instance got.
So if the model decided to color object A blue, this loss would kind of penalize it if pixels that aren't part of object A also end up blue.
Exactly that. It uses a specific type of loss based on saturation that focuses on color differences, especially for instances that are close to each other spatially. And they also added a clever term, strt-asii, that gives a bit more weight to making sure smaller instances are well separated.
Because small objects might be harder to distinguish otherwise.
Yeah, they could easily blend into similar colors if you're not careful. This helps ensure they stand out.
Okay, and the third component?
That's the mean level separation loss, math-cath mean. This takes it one step further. It specifically pushes the average colors of different instances apart from each other, so not just pixel-level separation, but overall color distinction between whole objects.
Okay, let me see if I've got this. Mathcol makes colors uniform within an instance. Mathcol Grader pushes nearby non-instance pixels away from an instance's color. And Mathcol Grader pushes the average colors of different instances away from each other.
Yes, that's the combination. Mathcol grammar plus mathmember plus lambda plus lambda mathrems mathbermean.
These three terms, working together, they allow the model to learn to segment objects purely by learning to color them distinctly and uniformly.
Wow.
It's guided by the ground truth instance masks, sure, but without any pre-assigned colors or category information in the loss itself. It's a really neat way to translate the segmentation task into the generative model's native language image generation and then structure the training signal effectively.
And the reason they think this works so well, the central hypothesis here, is that these massive generative models, things like Stable Diffusion or MAE, have already learned this fundamental grouping mechanism during their pre-training phase.
Exactly. Like, to generate a realistic image, you have to understand what makes an object, where its boundaries are, how textures fit together, how objects relate spatially. That understanding isn't just for creating images. They're hypothesizing it's a powerful prior for understanding them too.
Right. They learned a kind of world model of visual structure just by learning to generate pixels coherently. And to test this, they fine-tuned two specific types of large generative models using this gen2seg approach and their novel loss.
First up, the obvious candidate, Stable Diffusion, SD. We all know this one, text-to-image powerhouse. They took a pre-trained SD model and basically fine-tuned its UNet architecture part.
Yep, but the second choice is arguably even more telling. Masked autoencoder, MAE. MAE learns differently, right? It reconstructs images where large chunks have been blanked out. It has to fill in the gaps, which also requires a pretty deep understanding of image structure.
And the critical point about this specific MAE model they used, the MAE-BH versions, what was its pre-training data again?
It was pre-trained solely on ImageNet 1K. Now, that's a massive data set, sure, but it's just unlabeled images.
Yep.
It doesn't have the, internet scale diversity or the explicit text conditioning that models like Stable Diffusion got during their huge multi-billion image pre-training runs.
So if the MAE model also shows strong segmentation performance in generalization with this gen2seg method, it strongly suggests that the power isn't just coming from seeing literally everything on the internet or from text prompts helping out.
Yeah.
It's coming from the fundamental generative pre-training itself, that process of learning to synthesize pixels and understand their relationships.
Exactly. The ability to predict and reconstruct visual patterns seems to build this powerful structural understanding almost as a side effect.
Okay, and then there's the next kind of surprising piece.
Yeah.
The data they used for actually fine-tuning these models with the instance coloring loss was incredibly specific, like really narrow.
Yes, it was exclusively synthetic. They used a mix of HyperSim, which has these indoor architectural scenes, lots of furniture.
Right.
And Virtual Kitty 2, which is basically simulated driving scenarios, so lots of cars.
And this is crucial. The dataset contained ground truth instance masks for only indoor furnishings.
Yeah.
Beds, tables, chairs, sofas, things like that. And cars. That's it.
Meaning it specifically lacked masks for incredibly common everyday objects. Things like humans, animals, bicycles, traffic lights, food thing. Basically, most of the visual world we actually interact with.
Okay, so they train these powerful generative models on a relatively small amount of synthetic data covering a very narrow range of object categories,
Using that really clever coloring loss.
which then sets up the most remarkable finding: zero-shot generalization.
This is the real test, right?
Right.
Can the model segment objects accurately if it has never seen a segmentation mask for that specific object type or style? Not during its initial massive pre-training, especially true for MAE, and not during the focused gen2seg fine-tuning either.
And they designed a pretty rigorous set of tests using diverse evaluation datasets to really check this.
Oh yeah, absolutely. They didn't pull any punches here. They used EOCO, which takes objects from the standard COSEO dataset, but specifically excludes any categories seen in their narrow fine-tuning data.
So that tests generalization to common unseen stuff like people, animals, buses.
Exactly. Then there's DRAM, which is wild. It's a dataset of fine art paintings, impressionist, cubist, surrealist styles, a really severe test of style generalization.
Wow. Okay.
Then EgoHost, which tests generalization to those challenging, often blurry, super dynamic first-person video frames. They have unique distortions and motion blur.
Right. Totally different viewpoint.
Right.
And critically, iShape. What's that one about?
iShape evaluates performance on objects with extremely complex fine structures. Think wires, fences, mesh objects, maybe even detailed patterns on things, stuff that's hard to trace perfectly.
Okay.
And finally, PIDRE, which takes it completely out of the natural image world. It's luggage X-rays, segmenting small, often overlapping, kind of semi-transparent objects inside an X-ray image.
Wow. Okay, those data sets cover such a huge range of challenges: unseen categories, unseen styles, difficult perspectives, really fine details, even non-natural domains. It really puts the model through its paces to see if it learns something universally applicable about just objectness.
And the results? Well, looking at Table 1 in the paper, where they compare performance, they use MIOU at a single prompt point as the metric. It's genuinely surprising.
Well, this is where the hypothesis really seems to hit home.
Right.
The gen2seg models, particularly the fine-tuned stable diffusion and the larger MAEH, they achieved performance that approached, sometimes matched, or even slightly exceeded the heavily supervised segment, anything model, on these unseen object types and styles.
Yeah, and just think about that scale difference again. SAM was trained on 1.1 billion masks, billion with a B, spanning super diverse categories. gen2seg was fine-tuned on, 3.7 million masks? A tiny fraction of that, and only for furnishings and cars. Yet, it could segment humans, animals, objects, and paintings almost as well, or sometimes even better, than the model trained on billions of examples, including those very things.
And that outperformance on iShape, the fine structure data set, that's particularly striking, isn't it?
It really is.
It suggests there's something about the generative process, maybe this need to understand really precise pixel interactions to synthesize convincing details, that makes these models exceptionally good at drawing those intricate boundaries. Better perhaps than models like SAM, which sometimes might smooth over or leave gaps in really fine details.
Yeah, it feels like that pixel-perfect synthesis capability is directly transferable to pixel-perfect boundary detection. And another really key piece of evidence comes from comparing it to the discriminative baselines they tested, like SimpleClick and DynoB.
Right, because even SimpleClick, which was trained on the exact same synthetic data as gen2seg,
it performs significantly worse on all these zero-shot tasks. That really helps isolate the power of the generative pre-training. SimpleClick, which is a good segmenter but built on a traditional discriminative foundation, just couldn't generalize from that limited synthetic data in the same way the models leveraging a generative prior could.
And the MAE results, showing it could generalize segmentation to totally new domains and styles far beyond what it saw in ImageNet 1K, that feels like powerful confirmation that the generative prior itself is the key ingredient here, not just brute force data scale or text-image pairing from the web.
So the paper offers a theoretical explanation for why this might be happening, why generative models might generalize better in this way. It revolves around this concept of equivariant versus invariant representations.
Okay, let's dig into that a bit more. This feels like a slightly more academic point, but it sounds crucial to their whole hypothesis.
It really is. So traditional discriminative models, the ones often focused on classification or detection, they tend to learn invariant representations. Think about recognizing a cat. The model wants its internal cat feature to be the same, regardless of where the cat is in the image or how it's rotated or the lighting.
Right.
The representation is invariant to those kinds of changes, which is great for just saying, yep, there's a cat.
But maybe not so great for saying, Draw a precise line around this specific cat instance located at these exact pixel coordinates.
Exactly. For pixel-level tasks like segmentation, you ideally want equivariant representations. What that means is, if you make a change to the input image, say, you shift the object over to the right, the model's internal representation of that object, including its shape and location info, should change in a predictable corresponding way. The representation is equivariant to the transformation.
Ah, okay. So the model's internal map or understanding of the object actually moves or changes with the object in the input image.
Precisely. And the argument is that generative models, well, they must learn equivariant representations to some significant degree.
Why must they?
Because to successfully generate an image where an object is at a specific location with a specific pose, the model's internal process has to map those desired output properties back to features that can synthesize the correct pixels at the correct location. It requires an internal understanding that's sensitive to spatial layout and structure, basically, an equivariant understanding.
Got it.
And they hypothesize that this inherent equivariance developed during the generative pre-training is why these models are better equipped for tasks needing precise spatial accuracy, like instance segmentation, even when fine-tuned on limited data.
That makes a lot of sense. And beyond just the core segmentation performance, they also found some really cool, almost unexpected emergent behaviors from these fine-tuned models, didn't they?
Yeah, like the compositional scene representation they observed. So even though they weren't trained on object parts at all, the models would sometimes assign very similar, but maybe subtly different colors to parts that belong together compositionally. Like Darth Vader's mask and his body armor might get related colors.
Interesting.
It suggests they learned some kind of hierarchical understanding of visual components just from doing the instance coloring task.
And the zero-shot edge detection, too. Apparently, you could use the model's features to extract object boundaries, and the gen2seg models actually showed higher precision than SAM at low recall levels.
Yeah, indicating the boundaries they did find were often very accurate, very crisp.
But wasn't perfect. Right.
No, definitely not a perfect edge detector out of the box. The paper shows some examples where it sometimes included things like complex cloud formations or patches of grass as part of the background boundary map, which is actually kind of interesting. It gives you a little window into how the generative model might be interpreting scene structure slightly differently than a human would in those really ambiguous texture-heavy cases.
So it's clear this approach is incredibly promising, but they're also upfront about the current limitations.
Yeah, the primary one they point out is that these models still struggle a bit with segmenting very small objects, especially on dense datasets like the small object categories within Kasuo.
And they have a couple of ideas why that might be.
Yeah, they suggest it could be partly due to biases inherited from the massive generative pre-training itself. You know, stable diffusion, often guided by text prompts, might naturally favor more prominent, larger objects in a scene. And MAE, trained on ImageNet 1K, tends to focus on the main, often centrally located object in those images. Plus, there's the resolution factor. They fine-tuned gen2seg at a lower resolution compared to SAM's typical 124 by 1024 input, which inherently makes it harder to resolve tiny details.
So future work might involve things like leveraging even larger generative models, maybe ones trained on more diverse data distributions, and perhaps training the gen2seg step at higher resolutions too.
That seems like the logical path forward, yeah. And the authors seem pretty optimistic that those issues can be addressed as the underlying generative models continue to improve.
And the broader implications of this research, they feel pretty significant.
Absolutely. I mean, it really demonstrates that the huge investment pouring into training these gigantic generative AI models isn't just for making cool pictures or videos. That learned world model can be incredibly valuable for foundational perception tasks, too.
Which points towards a future of much more data-efficient segmentation, maybe. If you can build on the immense knowledge already encoded in a powerful generative model, you might drastically reduce the need for those billion mask datasets every time you want to tackle a new domain or application.
Yeah, imagine the potential for fields like robotics or medical imaging analysis or autonomous systems. Places where detailed scene understanding is absolutely critical, but getting vast amounts of precisely labeled data is often super expensive, time-consuming, or even impossible.
The authors are clearly excited about this, suggesting that as generative models continue to scale and their pre-training data gets even more diverse, their inherent ability to parse and understand the visual world will only get stronger. And that could unlock even more capabilities for perception tasks down the line.
It really is quite a compelling direction.
So let's wrap this deep dive with the core takeaway from the Gen2seg paper. It powerfully reveals that generative models possess this surprising, inherent understanding of visual structure, things like object boundaries, compositions, fine details, spatial relationships. And crucially, this knowledge can be effectively transferred to challenging perception tasks like instant segmentation.
And the real innovation here is in reframing segmentation as that image-to-image translation problem, combined with that very clever instance coloring loss. That's what leverages the generative prior and enables this remarkable zero-shot generalization from surprisingly limited training data.
Okay, here is a provocative thought to leave you with. This work fundamentally suggests that these powerful generative models, simply by learning to synthesize the world, might be learning something deeper, perhaps even more universally applicable visual representations than models trained purely for discriminative tasks like classification or detection. So how else might we tap into this latent world model that seems to be learned by these generative giants? Could they hold the key to solving other fundamental problems in computer vision, maybe in ways we haven't even begun to imagine yet?
It certainly forces you to reconsider what we even mean when we say a machine understands an image.
It absolutely does. Thanks for joining us for this deep dive.